Do you want to become a world-class engineer? Do you want to nail every single job interview? Then this video is for you. Hey guys, Nachkazi here. In today's video, I'm going to do a deep dive into IPv4 routing. It's going to be a fun one because it's one of my favorite topics. It's the most fundamental and important topic in the realm of layer 3. We're going to look at how binary AND operation works. We're going to look at how ARP works, and we're going to look at how all of it comes together to allow the LAN and WAN communication to happen. Without further ado, let's roll. Welcome to CCNA 200-301 course. Today, I'll cover Section 3, Part 2, IP addressing and routing. We'll do a deep dive into IPv4 routing. Here are the topics I plan on covering today. First, IPv4 routing overview. Second, fundamentals of IP routing. And finally, I'll wrap it up by providing a quick overview of different types of static routes. First, let's look at IPv4 routing overview. What is routing? At a very high level, routing is about forwarding packets from the source to the destination. If you guys remember the OSI model, IP addressing lives at layer 3 of the OSI model, at the network layer. And routing is all about sending packets from one device to another device. So if we were to look at this topology here, in this instance, Bob at the top wants to send an email to Sal at the bottom. What Bob will do is, it's going to be the source because that's where the email is originating. And Sal will be the destination. So from a routing perspective, in order for Bob to be able to successfully send an email to Sal, he's going to need to do IP routing in order for him to be able to successfully deliver the email message. Now, I'm going to come back to this slide momentarily because there's a bunch of concepts that I would like to clarify as we continue moving forward. Now, the type of routing we're going to be talking about here today is called unicast routing. There's also something called multicast routing. That's a topic for another day. Today, our goal is to focus on unicast routing, and routing is based on destination. It's all about getting to the destination. So if you think about, the best analogy I can give you is a GPS. If you have ever fired up and used a GPS on your smartphone, then you know that when you do that, you become the center of the universe as an individual. So you become the source. And where you want to go, the destination you want to get to is the destination, right? So similarly, each layer 3 device in our network that needs to send information to another device ends up becoming the source, and the other device on the other end is the destination. And that's what routing is all about. Now, layer 3 devices include end hosts. So that's your PCs, IP phones, printers, IP cameras, any type of device that is able to communicate IP. That also includes switches and routers and firewalls, etc. must know where the destinations are, right? So every single hop. So for example, if I'm in San Jose and if I want to send an email to somebody who's in New York, well, physically there's going to be a bunch of routers in between us. And every single device, every single layer 3 hop between San Jose, California to New York needs to have information about the destination so it can actually route my traffic to the eventual destination, which in this case is Sal. And once again, I'm going to come back to this slide because there's a couple of concepts that I would like to crystallize. So what ends up happening is, how did Bob know how to send information to SAL to begin with, where there's something called a binary AND operation that is ran on the devices. And all layer 3 devices run this binary AND operation. The first thing that happens when that operation is ran is the layer 3 device looks at its own IP address and its own subnet mask and run the binary AND against it. Then what it does is it takes the destination IP address and its own subnet mask and then runs a binary AND against it. And if the resulting value is identical, then that means we're on the same subnet. And if that's the case, then the traffic is sent directly to the destination. If the resulting value is not identical, then that means we are on different subnets. And in that case, the packets are sent to the local default gateway. Now, to continue building on this, there's something called a binary AND operation logic truth table. That tells us how the overall binary AND logic actually works. So let's quickly take a look at it. Let's assume value A is the IP address and value B is the subnet mask. What ends up happening in this case is that we look at the binary number, whether it's 0 or 1, right? Binary is either a 0 or a 1. So if the IP address is 0, and if the bit on the subnet mask side of the house is 0, then the end result is 0. If the binary bit is 0 for IP and it's 1 for subnet mask, the result is still 0. And remember that there is an implied AND because we're looking at the AND operation inserted in between A and B. So it's the binary AND operation. If the IP address is 1 and subnet mask is 0, then the result is 0. If IP address is 1, if the subnet mask is also 1, then the result is 1. So if you look at the two bullets at the bottom here, if both inputs match 1, the result is true and the value is 1. In all other variations, the result is false. So that's how the binary bit logic works. Now, under this context, let me take you back to the first topology that I was showing you earlier to help crystallize how this works. So if you were to look at these two IPs here, Bob wants to send an email to Sal, right? So Bob's IP is 172.16.0.1 and it wants to communicate with 172.16.0.2. Well, what did we learn? What we need to do first is we need to look at the source IP and we need to run a binary AND against it. So what that means is, let me do quick whiteboarding. 172.16.0.1, this is Bob's IP, right? And the subnet mask is 255.255.255.0. Well, we need to look at these from a binary perspective. So what's 172 in binary? So let's quickly do the binary math here. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. If you guys remember the binary decimal conversion chart, that's what I'm going to explain here. But I've done that already in my last video. I'll provide a link up at the top. You can either tap or click on it, and you can go and look at that video that I did. So you can learn at a much deeper level how this works. But here I'm just giving you a quick overview. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, 4, 8, 16, 32, 64, 128. And if you were to draw a line here, what we want to do now is look at 172.16.0.1. So we're going to have to look at each octet here in this IP address and map it to this binary conversion chart. So what's 172 in binary? Well, let's figure that out. So if the first bit If the 128 bit is set to 1, if the 64 is also set to 1, it's gonna go over 172, so we're gonna have to set that to 0. 128 plus 32 is 160. So this is also gonna be 1. If we also enable 16, that would be too much. It's gonna go beyond 172, so we're gonna have to set that bit to 0. The one right next to it is 8, so a total of 168. We need to get to 172. Well, this bit, if you also enable this bit and set the rest of the bits to 0, we'll get a decimal figure of 172. How about 16? Well, let's do that as well. So 16 means these bits are going to be off, 16th position is going to be on, the rest are going to be all zeros. What about 0? Well, that's a very simple one. It's going to be all zeros. Love the simplicity. And then what about 1? Well, it's going to be all zeros followed by a 1. So now, let's take this binary math and line it all up. So let's do that. 1 0 1 0 1 1 0 0. That's 172. What about 16? 0 0 0 1 0 0 0 0. What about 0? It's gonna be 8 zeros. And then what about 1? It's gonna be 7 zeros. 6 7 followed by 1. And then what about 255? Well, 255 means all the bits are on. So we're going to do that. 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. And then 0 means it's going to be all zeros. Well, what we need to do now is we need to very quickly here look at the end result. So if you guys remember the binary logic, the truth table, 1 and 1 is 1, but 1 and 0 will always be a 0. 1 and 1 is 1, 1 and 0 is 0. 1 and 1 is 1, and 1 and 1 is 1, 0 0. Then we get 0 0 0 1 0 0 0 0, then a bunch of zeros in the third octet, 4 5 6 7 8, 1 2 3 4 5 6 7 8. So what this gives us, if we were to convert this into decimal, is 172.16.0.0. So that means that this is our network address. And that was the whole point of Bob's PC running this binary AND operation in the background. All it was trying to do was trying to determine its own network address. So it knows that its network address is 172.16.0.0. So now let me go back to the slide we were looking at. So it knows that the network address is 172.16.0.0. So that's first step, right? So Bob's first step is to determine its own network address. Second step is to take the destination IP and run it against its own subnet mask. So that's step number 2. Well, let me save you some math and let you know that the end result is going to be the same, which means they're both on the same subnet. And because both PCs are on the same subnet, Bob now knows that it has the ability to communicate directly with Sal without having to go through an intermediary gateway device. So it doesn't need a default gateway. Bob can communicate directly with Sal, because in between we got a layer 2 transport network, which is seamless to Bob. It might as well be a one long wire running from Bob's PC all the way to Sal's PC. So that's the level of transparency that we're getting from these switches here. And that's how the binary AND operation works. Now there's one more concept that I want to clarify, and that is, if you guys recall, and I want you to picture the OSI model in your head, At layer 3, at the network layer, that's where IP addressing lives, right? And IP addressing is basically logical addressing. And at OSI layer 2, that's where MAC addressing lives. Well, we have to map the two together in order for the communication to occur. And the way it happens is through a protocol called ARP, or Address Resolution Protocol. And all layer 3 devices on our network maintain an ARP table, which is a mapping of an IP address to a MAC address. And ARP allows us to create a new layer 2 frame. It's also called layer 2 packet rewrite. But before I go too deep into this, I'm gonna actually give you an example of how this works. Until then, let's park it. Always remember that ARP request is a broadcast, whereas ARP reply is a unicast. And we just talked about the binary AND operation, right? The whole idea of running the binary AND operation by the layer 3 devices in our network is to determine who to ARP for, because ultimately we need to decide, are we ARPing for another device on our local subnet? And how's that determined? Well, if the destination IP matches my subnet when I run the IP AND operation, then that means the final destination is local to me. So I'm gonna ARP for my final destination locally. But if the destination IP doesn't match my subnet, then that means I need to go and talk to my default gateway or a router in the middle, also known as intermediary router, and let that router figure out to get me to the final destination. And one final thought, guys, before I go back and explain to you using the topologies you were looking at earlier, this ARP process is repeated at each layer 3 hop throughout our network. So if there are 10 routers in the middle, every single router in the middle of our source and destination is going to run the ARP process, assuming it's an Ethernet network. Now let me quickly go back to the topologies and explain how this works. So now I'm going to be very quick. Step number 1, I'm sure you guys remember at this point, Bob's PC has to run a binary AND against its own IP and subnet mask. It finds out that it's on subnet 172.16.0.0. Second step, it takes Sal's IP and its own subnet mask and runs the same AND operation, and it finds out that Sal also happens to be on 172.16.0.0. Well, what it finds out by running these two operations is that they're both on the same subnet, and because they're on the same subnet, Bob ARPs for the destination directly, which happens to be Sal in this case. And let me quickly explain a quick review of how ARP works. In order to understand how ARP works, let's quickly zoom into an IP header or an Ethernet header. So what an Ethernet header would contain is the layer 7 information, which happens to be email in this case. Then we'll have the layer 4 header information like TCP. In this case, we'll have the layer 3, and then we'll have the layer 2. Now, if we were to zoom in to layer 3, we're going to have the source IP of Bob. We'll have the destination IP of Sal. However, when we look into layer 2, we'll have a source MAC of Bob, because Bob is the originator, and then the destination MAC of, if you were thinking Sal, you would be incorrect. It would actually be, if they're talking to each other for the first time, they've never communicated before, then what's going to end up happening is the destination is going to be set to all Fs. by Bob. And all Fs is basically a layer 2 broadcast. So every single device on that VLAN at layer 2 or that subnet at layer 3 is gonna get that broadcast. Well, in this case, the only other device on this network is SAL. So SAL is gonna get that. It's going to look into layer 2 and layer 3, and by looking at layer 3, it's gonna see that the destination IP is itself. It's gonna realize that this message is meant for him. He's gonna go ahead and respond back to Bob by providing its own MAC address, which ends in B. And Bob will get that, and Bob will build its ARP table. SAL will also update its ARP table. What that also does for us in the middle is that switch 1 and switch 2 will also build their MAC address tables when this happens. And let me quickly show you the CLI of how this looks. So here I am on Bob's PC. I'm gonna do ipconfig/all. By doing that, I'm looking at a couple of different things here. First of all, I'm gonna focus in on Fast Ethernet 0. That's the main interface I care for. My IP address, my subnet mask, and my physical address, which ends in .a. So that's Bob. Now let's also quickly take a look at Bob's ARP table. And Bob does not have any entries in its ARP table at the moment. Let's go ahead and quickly check out SAL. So here I am on SAL. I'm gonna do ipconfig/all. And when I look at the Fast Ethernet 0, I see that my MAC address ends in B, which matches the diagram. The IP address matches, and the subnet mask matches. Now, let me also quickly take a look at the ARP table on this PC. And there are no ARP entries. Now let me go ahead and ping on Bob's PC. I'm gonna go ahead and ping SAL. So 172.16.0.2. And it's successful. Beautiful. Let's quickly look at our ARP table again and see this time around our ARP table is populated. And as a matter of fact, not only we can see the IP address of SAL, but we see the physical address that ends in B also being populated here. And now that we have the ARP table built, Bob will have the ability now to construct a layer 2 frame and start sending information directly without using any other intermediary layer 3 device. And this is actually called transparent bridging, this whole process, because we're not using any other layer 3 device in the middle, and the switches are not manipulating any data. They're not changing the layer 2 header information. The layer 2 header information stays intact between Bob and SAL. And this is what's known as transparent bridging. Now let's quickly take a look at the other topology where we have a router in the middle to kind of go a little bit deeper into this stuff. Now in this example here, we've got two separate subnets. We've got a subnet on the left and we got a subnet on the right. And I have this imaginary kind of dotted line in the middle to differentiate between the two subnets. Now, if you look at Bob's IP and if you look at SAL's IP, on the surface, you might think, well, 172.16.0.1 and 172.16.0.17, they gotta be on the same subnet, right? That's what it seems like. Well, but pay very close attention. You see the /28. It's not /24, it's /28, which makes the overall subnet very small. What's /28? 255.255.255.240. So it only gives us 16 possible IP addresses in the network range, and out of 16, if we were to subtract 2, because we can't use the network address and the broadcast address. The very first address in any IP range is a network address, and the last one is a broadcast address. And we cannot use them based on the IP rules. We end up getting only 14 usable IPs in each of these subnet ranges. And that's what we're seeing here. I wanted to trick you a little bit. I wanted to see if you were actually paying attention. And guys, just taking a step back here, remember, network engineering is all about paying attention to detail. At the end of the day, unless you pay attention to detail, you're never going to become a good network engineer. That's the number one trait that you need to develop as a network engineer, paying very close attention to every single thing that's happening on the screen, to the topology, to the configuration of the devices, everything, to make sure everything properly matches. So that being said, now let me explain how this scenario is going to play out compared to the previous scenario where we didn't have the router. So in this scenario, Bob wants to send an email to Sal. So what's going to end up happening is Bob's PC is going to run a binary AND operation against its IP and subnet mask. And it's going to realize that it's on a network 172.16.0.0/28. Next, it's going to take Sal's IP address, which ends in .17, and run a binary AND against its own subnet mask of /28. And what it would realize, and let me save you a lot of math and time here, is that it's on 172.16.0.16/28. Because these two subnets do not match, there is actually a mismatch. What ends up happening in step 3 is that we send packets to the default gateway, which in this case happens to be the router here. But before we do that, we need to ARP for the default gateway. And when we inspect the ARP packet, that's what we see. We see the payload, which is data. We see layer 4 information, which in this case would be TCP, SMTP in particular, because this is email. And then we'll have layer 3 and layer 2 header information. If you were to zoom into layer 3 header information, we'll have the source IP of Bob's PC. We'll have the destination IP of Sal's PC. We'll have the source MAC of Bob's PC. And the destination MAC is going to be set to what? All Fs, right? Because we just finished talking about ARP. So initially it's all Fs, which is a layer 2 broadcast. And it's sent out to all the hosts on the same VLAN or all the hosts on the same subnet at layer 3. Everybody gets it. Only the device that is supposed to respond back is going to respond back. And at that point, these all Fs in the subsequent packets will be replaced with router's interface number 1. The interface pointing to the Bob's PC here. This interface right here. The next thing the router is going to do is it's going to realize that the destination IP is pointing to Sal's IP. And lucky for the router, Sal's IP happens to be directly connected on router's interface number 2. So what it's going to do is it's going to go ahead and decapsulate the packet and re-encapsulate it. And I'm going to explain the process in a moment here. But when it goes ahead and does that, it's going to retain the data, the layer 4 information, and the layer 3 information. The only thing that it's going to change is it's going to go ahead and rewrite layer 2 header. Because remember, we're swapping interfaces here. So because the interfaces are being swapped, it has to do what's called a layer 2 packet rewrite in order for the packet to be transported across 2 different networks and 2 different interfaces. Now, if we were to zoom in to this packet right here, here's what we're going to see. The source IP of Bob's IP, source IP didn't change. Destination IP didn't change either. This is Sal's IP. But what did change is the source MAC. In this instance, the source MAC is going to be router's interface number 2. And the destination MAC in this instance is going to be initially all F's because it has to determine Sal's MAC address and all that. So it's going to go through the whole jazz that I've discussed so far. And eventually it's going to get Sal's MAC address back. It's going to populate its ARP table, and all the consequent packets are going to have the destination MAC set to Sal's MAC address. And now at this point, there's sufficient information for the router to be able to go ahead and send traffic. Now, another thing that the router had to do behind the scenes is it would actually have to look into the layer 3 routing table because it's 2 different subnets. So it's going to look at the source subnet and the destination subnet and its routing table, and then formulate the packet accordingly, which is the layer 2 packet read-write process, so the information can flow from one end to the other. Now, another thing to keep in mind is Sal's PC also has to do the same thing in reverse in order to be able to find its way back to Bob's PC. Because remember, it's a per hop idea, and it's also a directional idea. So each direction, so from Bob's perspective, we have directionality that is pointing us into Sal's direction. But then the opposite is also true. Sal has to go through the network in order for it to be able to find its way back to Bob. So naturally, it has to go through the exact same process of running the AND operation on its IP, then running the AND against Bob's IP, using its own subnet mask, and then it's going to have to ARP for the default gateway, and the same thing is going to have to be repeated all over again. And eventually the ARP tables are going to be built end to end. The router in the middle is going to have its ARP table populated for both sides of the subnet, and we're going to have end-to-end connectivity. So now that we understand the mechanics of IP routing, we're going to quickly take a step back and do a 10,000-foot overview of the fundamentals of IP routing. There are 2 components of IP routing. First is determining the optimal path, which is called the routing protocol, and the other is transporting packets through a network. That's called routed protocol. Now let's quickly zoom into each. Routing protocols are used to establish a communication channel that helps the layer 3 device or router determine the best path. Examples are routing information protocol, enhanced interior gateway routing protocol, open shortest path first, intermediate system to intermediate system, and border gateway protocol. Routed protocol, on the other hand, carry the actual data. They are the ones that are carried across the network. Examples include IPv4 and IPv6. Now, a very quick analogy that I can give you that helps me understand these protocols very easily is you can think of a routing protocol as a road, like a highway. And what you have on a highway is a bunch of cars. You may have the big cars, a big truck, different type of vehicles, right? Those vehicles you can consider as the routed protocols, whereas the road itself could be considered a routing protocol, because road is what's providing the communication path, the transportation path. If you want to go from San Jose, California to Chicago, Illinois, the path you take is the routing protocol. But the vehicle that you're using to get there is the routed protocol. So hopefully this kind of crystallizes the concept in your head a little bit. What's the job of a routing protocol? Let's quickly talk through that. First, IP protocol learns IP routes from neighboring routers. Second, it advertises IP routes to the neighboring routers. Third, if more than one path exists to one destination subnet, the routing protocol picks the best route based on a metric. If something changes in our network topology, meaning a circuit goes down or a link failure, interface dies, we remove the path from our local routing table. That's what the routing protocol does. Then it advertises the change so everybody else in the network knows that, hey, this link went away. Don't use this path because it's dead. And instead, we look for an alternative path. Now, these three last steps that I just talked about, this process is known as convergence, where interface went down, we advertise the change to others so everybody knows that the network is down. And then we do a quick calculation to figure out how to route to the same destination using a different path. That's called convergence. There are two major categories of routing protocols. First is called interior gateway protocols, or IGP. That's the type of routing protocol that's used inside a single autonomous system. An autonomous system is a single administrative domain. So you can think of it as the company you work for. It's a single organization. So that would be considered a single autonomous system. And the examples of IGPs include RIP, EIGRP, OSPF, and ISIS. EGP, on the other hand, or exterior gateway protocols, is where you have different autonomous systems in the mix. And the administrative domain here is multiple organizations instead of a single organization. And there's only one EGP on planet Earth. It's called BGP, or Border Gateway Protocol. So here's a quick real-world view of how IGPs relate to EGPs. So let's assume I have this company called Notch Corp, and my very first location opened up in San Jose, ended up becoming a data center. This is the public IP that I have, and I'm running OSPF internally between the routers. So this becomes one autonomous system. And then I have another location, that's another company that I just bought in Chicago. And this is the public IP that I have for this location. And I'm internally running EIGRP between the routers to route. As you can see, San Jose is running OSPF, but Chicago is running EIGRP. It doesn't really matter because each of them are their own domains, right? Administrative domains. So that would be considered an IGP operation here within this cloud, IGP operation here within this cloud. And what each cloud has is a leg, an internet circuit into a service provider. So Chicago has an internet circuit into an ISP, and so does San Jose. And there's a BGP peering that we have with the service provider routers. And Chicago connects to ISP1. ISP1 internally runs OSPF. ISP2, on the other hand, that's connected to San Jose, runs ISIS. And then the ISPs interconnect with each other over BGP. And then there are different autonomous system numbers. As you can see, Chicago has the autonomous system number of 111. ISP1 has BGP ASN of 222. ISP2 has BGP ASN 333, whereas San Jose has BGP ASN of 444. Now, a couple of things I want to bring to your attention. So each one is running an IGP, each cloud, within their own administrative domain. But the common thread that interconnects everything, as you can clearly see, is the BGP. BGP is the thread that interconnects all of these sites together. And BGP is how the internet exists today. Internet wouldn't exist if it wasn't for BGP. So BGP is an amazing and very powerful routing protocol that allows the whole world to connect with each other. And that's the difference between IGPs and EGPs. Now, a quick tidbit for your information, we can get public IPs from an organization called ARN, American Registry for Internet Numbers. And we can get public IPs from ARN. We can also get, these would be IPv4 IPs, of course. You can also get IPv6, but IPv6 that's a topic for another day. And we also get BGP ASNs from ARN as well. And these are public BGP ASN. You can also have a private BGP ASN, but that's beyond the scope of this exam. But here, both BGP ASN and public IPs can be obtained from ARN in North America, but then other regions like APNIC for Asia, and there are others for Europe and all that, you basically go to those local authorities to obtain the IP addresses and BGP autonomous system numbers. Now, that's just a little tidbit. It's not necessarily related to IGP and EGP, but I just wanted to throw it out there for some real-world knowledge. Now let's quickly take a look at routing classification and types. There are two routing classifications: classful routing, type of routing that does not have support for VLSM. This is the old school, like class A, B, C. Watch my previous video to learn more about these classes. Classless routing, on the other hand, supports VLSM, which stands for Variable Length Subnet Masking. And the examples are RIP, EIGRP, OSPF, BGP, and ISIS. Routing types. There are two different types of routing. Static routing. This is how we manually type in the routes. And it's designed to define fixed paths. It works well in small environments where traffic is predictable. The other one is called dynamic routing. That's the preferred mechanism. That's the type of routing in which routes are learned auto-magically. Dynamically adapts to the changes in the environment. And the internet wouldn't exist today if it wasn't for dynamic routing. And examples are BGP, OSPF, all these routing protocols are dynamic routing protocols. Whereas if you were to manually type in a static route command, that would be considered static routing. There are different types of routing algorithms. First, distance vector. Distance vector protocols are also called Bellman-Ford algorithm, named after their inventors. They send routing updates to their neighbors. Distance vector protocols send large updates to the neighboring routers. Each node running distance vector protocol only knows about its neighbor. Distance vector protocols conduct routing by a process called routing by rumor. So what that means is, if the neighbor is advertising false information, we'll accept it, because that's what routing by rumor means. If it's a rumor, it's a rumor. We don't know any better. Because our neighbor is saying it's truth, we'll assume it's true, and we'll advertise that information to the rest of the environment. Examples include RIP, IGRP, EGP, and BGP. Link state. Protocols, also known as shortest path first or SPF algorithms, they flood routing updates to all the routers in the entire network. So the idea here with link state is that all the nodes, all the routers in the entire environment know about everybody else. And small updates are sent to the routers in link state because everybody knows about everybody already. And each node has an entire picture of the entire network. And the examples include ISIS and OSPF. Link state routing protocols are taxing on the routers and layer 3 devices that these protocols are running on, because each device, each node needs to have an entire picture of the entire network. So something to keep in mind. The final type is called balanced hybrid or advanced distance vector. They have characteristics of both distance vector and link state. Hybrid routing protocols send only incremental updates similar to link state, but only to its neighbors like distance vector. Example includes EIGRP. Now, how does routing table work? Let's quickly talk through the decision-making process in the order of operation. So the order of operation that I'm going to show you here is important. First order of operation is prefix length. The longest prefix match is the best and most specific route and is always preferred in the routing table. This criteria has the highest preference and it trumps all other route attributes. The next thing that the router looks at, if the prefix length is the same for different routes in our routing table, is administrative distance. If there are multiple routes to a destination with the same prefix length, the route learned by the protocol with the lowest administrative distance is preferred. Administrative distance is locally significant and does not get advertised, and lower number is considered better. So lower AD equals high priority. Administrative distance can be manually manipulated as shown below. So for example, here's a sample config, right? So if you're in a router, we can type in router OSPF 1, and then under the router OSPF configuration, we can change the distance to 70, for example, and that would change the administrative distance of the OSPF routing protocol on that router. And the final criteria is metric. And if the administrative distance, subnet mask, and prefix length are all the same for multiple routes, then the lowest metric is used to choose the best route. RIP uses the metric of hop count, OSPF uses the metric of cost, and EIGRP uses what's called a composite metric or K values, and the default is bandwidth and delay for EIGRP. If administrative distance, subnet mask, and metric are all the same, then the router starts load sharing on that link. Now let's quickly take a look at the administrative distance table. And here are the default values. Connected interface has an administrative distance of 0. Static route has an AD of 1. eBGP has an administrative distance of 90. EIGRP has an AD of 90. OSPF 110, ISIS 115, RIP 120, and unknown is set to 255. Now, administrative distance is the believability. So the connected interface is always the most predictable and the most believable because that is literally connected to the router, right? It's physically there or logically there. Static route is a route that an administrator manually types into the router. That's also pretty believable. But as you can see, with dynamic routing protocols, the believability decreases with different types of routing protocols. So that what that means is if we have static routes configured on our router, most likely our static routes will be considered preferred over the dynamic routing protocols. Now, let's quickly look at IGP comparison chart. So there are 6 different features that I want you to look at. First of all, these 3 routing protocols, they're all classless. RIP version 2, EIGRP, and OSPF. From an algorithm perspective, RIP version 2 uses distance vector, EIGRP uses advanced distance vector, and OSPF uses link state. They all support manual summarization. RIP version 2 is vendor agnostic, meaning it's multi-vendor supported. So is OSPF. EIGRP, on the other hand, used to be Cisco proprietary. The reason I have an asterisk here is because in 2013, EIGRP was made public, meaning other vendors can now also implement EIGRP in their code and in their network operating system and run it. But I think Cisco took so long to actually make that happen that I don't think there's any adoption in the industry. Like, in other words, nobody really cares to implement EIGRP in their routers. Cisco should have done it a long time ago, and EIGRP had just come out. But you know, it is what it is. Routing updates are sent to a multicast IP address on all three. And from a convergence perspective, RIP version 2 is slow. EIGRP is very fast because it has a concept of successor and feasible successor, which means it has the primary path and the secondary path in the routing table available all at the same time, and it doesn't have to recalculate. It's very, very fast, so switch over. And OSPF is considered fast. Now let me give you a quick overview of static routes. So a static network route or static route is composed of two different pieces. Piece number one, it's a manually configured route that defines a subnet or an entire class A, B, or C network. Next, you can either specify an outgoing interface or a next hop IP. So here's how the syntax looks. On the router, and we'll do this in CLI in a moment, here's what we type in. On the router, we type in IP route. We specify the network that we need to specify. We specify the subnet mask of that network. And then finally, we specify the next hop IP address. So the next hop IP, this is the subnet mask, this is the network address, and then these are the keywords, IP route. And that's how we create a static route on a router. Here's another example where instead of the next hop IP, we have the local interface specified. Specifying the next hop IP in the static route is considered a best practice design. Specifying an Ethernet interface, for example, is not considered good because if it's a point-to-point interface, you're fine. But if it's not a point-to-point interface and if it's like an Ethernet segment with multiple devices on it, every single time you're expected to route traffic to that interface, it's going to generate a broadcast, and that broadcast will be sent out to all the devices. So it's not considered good practice to specify an interface. Instead, you should always have a next hop IP configured. Reviewing the show IP route command shows a different output in the routing table for each of the static routes configured above. So what I'm saying is that for each of the IP route statements that we have specified here, whether we have the next hop IP or the interface specified, the output is going to look different. And I'll show you that in a moment. When the router interface associated with static route fails, the router automatically removes the static route from its routing table. So now let's quickly go to the CLI and look at this stuff. Now let's quickly take a look at this routing scenario here right in front of us. So about router 1 right now, and I'm gonna go ahead and take a look at show IP interface brief to see what's going on. And it seems like I have an IP address of 10.0.0.1 configured. See if I can ping the other side, which happens to be 10.0.0.2. And it seems like I'm able to successfully do that. So router 1 is able to ping router 2. Now router 2 happens to have a couple of different routes. 192.168.0.0/24 and 192.168.1.0/24. Two separate subnets behind its LAN. Now router 1 by default is not going to have the ability to see those routes. To verify that, we'll look at show IP route. This is the routing table. And as you can see here, routing table has this codes section. So what we can see right below that is the different networks that are in our routing table. And C corresponds to the flag or the code up here in the table, which stands for connected. So this right here is a connected route, and it's on our interface gigabit 000. And this happens to be the /30. Our local route which is the L flag here, is 10.0.0.1/32. Now this is called a host route because it's a very specific route. It's a /32. And it's also directly connected over Gigabit Ethernet 000. So if you guys remember the administrative distance chart we were looking at, this has an administrative distance of 0 because it's directly connected. It's considered to be the most believable. Now, we got a bit of a problem here. We cannot see the routes that router 2 has, these 192.168 routes. Now, before we do anything, let's quickly jump to router 2 and look at show IP interface brief, make sure everything is up and running. And indeed it is. And what I've done is I'm representing these routes as loopback interfaces because it doesn't really matter. I mean, I could have other layer 3 devices hanging off of this router if I wanted to, but I'm just trying to simplify the configuration here, and it doesn't make any difference whatsoever. Let's quickly take a look at show IP route. So if I do that, I will see that I have a bunch of routes that I've specified. Once again, for every route or for every interface, I'm going to see 2 different entries. One is the host specific entry, and that has a flag of L right next to it. And then I'll see another entry, which is the C entry, the connected route. And that is the network that I specified when I was configuring my interface. So let me quickly show you what I mean. So if I were to do show run, let me show you how I've specified these interfaces. Loopbacks are /24s, as you can see here. The Gigabit 000 is actually a /30 because it ends in .252. Now, if I were to look at the show IP route, the reason we're seeing the loopbacks with /24 and /32 is /24 represents the subnet that I typed in here, right, which was .0. But because I have specific IPs on the interface, it automatically inserts a host route. So this is not something I inserted. This is the operating system automatically inserting the host route just so it has a specific entry in its table. So I just wanted to quickly point out that distinction. Now let me jump back to router 1. We still have a problem. I can't ping, for example, one of these subnets that router 2 has on its LAN side. And I'll prove to you that I can't ping either one of them. Both networks are currently unavailable on router 1. And the reason is router 1 doesn't know where those routes are and hence is unable to get to those destinations. So let's go ahead and enter those routes manually. That's what's called static routing. We'll go ahead and set that up. So IP route 192.168.0.0. Then I'll type in the subnet mask, and finally I'll type in the next hop IP here, which for us is 10.0.0.2, which happens to be the router 2's interface pointing toward us. Now let's go ahead and do ping 192.168.0.1, and voila, we have much better luck this time around. Now, if you were to look at show IP route, you'll clearly see that we have an S flag, which stands for static, meaning I manually typed it in. And as you can see, it clearly spells out the network address, the subnet mask, and the fact that it has an admin distance of 1 and metric of 0. So it's very, very believable. Of course, directly connected will always be preferred, but then right after that would be the manually typed in static route. And it specifies the next hop IP that we typed in of router 2. Thanks for sticking around. By the way, there's a lot more to this video than what you have seen. In order to watch the entire video, you're gonna have to be a little patient because I'm working on designing an entire CCNA course. I'm gonna do an official launch in the next couple of months, but until then, I'm gonna keep putting little nuggets of the CCNA exam out there on my YouTube channel until the course is ready to be published. Hope you enjoyed today's video. If you did, give me a thumbs up, hit subscribe, and I'll see you in the next video.